Okay, so we're going to be going through some of the questions that were really important from Unit 6, Module 1. Part of this work part of these problems come from the Unit 5, Unit 6 practice exam that's on sapling, and other questions come from the homework from Unit 6, Module 1, and then there's a question in the quiz that many people had some questions about. All right, so let's take a look at this question in which we have PCA and we're given a PKB of 4.8, which means that here we have the reaction for PKB, and we see that this value is 4.8. And then they say this can be combined with CO3 2 minus, which has a PKB of 3.7. All right, so here's the reaction for PKB, 3.7. And so we have PCA in the reactants, we have CO3 2 minus in the products. And so the question asks, is this expected to be reactant favored or product favored? And so when we look at this in detail, we see that the PKB, the strongest substance here, the strongest base, is CO3 2 minus. We would expect that to react the most, meaning that, and as a product, that means that this would be pushing towards reactants. And so given that this is stronger, we would expect that in this chemical reaction, which has the strongest substance as a product or the most reactive substance as a product, we would expect it to be reactant favored. And we would pick this one. Okay, let's go to the next one. So here we have a chemical reaction. It's the same one, but now they're asking, okay, the pH is 9.5. Which of the compounds is the conjugate acid in this reaction? So we take a look at the analysis. We have an acid as in the reactants. We have a base in the products, as always. And as conjugates in the products, remember the products always contain the conjugates. We see an acid-base pair. The conjugates are here as products, and so the base would act as a base in the reactant, will act as an acid in the products. And we see that H2CO3 is the substance that's acting as the conjugate acid. So we would pick C. If we were going to make a table of the acid, base, and conjugate, here we would see that CO3 2 minus plays the role of a base. Its conjugate is an acid, HC3O minus. HN plus, which the molecule shown here, plays the role of the acid. Its conjugate is going to be the neutral amine. It's the base, conjugate base, and acid. Okay. So which of the compounds is acting like an acid? So we just answered that in the last slide. We see that CO3 2 minus is acting as a base. It has a conjugate acid. B, the molecule here, the protonated amine, is acting like an acid. It has a correspondingly neutral base. And so all the neutral amines, so if it's a conjugate base, that means it must have acted as an acid. The answer will be B. Okay, and here's a pretty straightforward question. What is the concentration of hydroxide ions in this solution with the pH of 9.5? So there's a couple ways it is. You'll be given access to this equation on the exam, and also this one that the concentration of the hydronium ion is equal to Kw 1 times 10 to the minus 4 divided by hydroxide ion. Here we're given the pH, so now what we can do is we can solve for the hydroxide ion by manipulating the relationship, and so now we have 1 times 10 to the minus 4 divided by 10 to the minus 9.5, right? That's going to be the concentration of H3O plus. We put that in a calculator, we see that value is 3.16 times 10 to the minus 10, which gives us 3.2 times 10 to the minus 5, which is one of the options. So you want to make sure you feel comfortable with this calculation. This will be very important as time goes on, as the problems get more difficult. All right, so here we have a chemical reaction that's dealing with treatment of blood pressure, and the experiments indicate that the decomposition is first order with respect to the concentration of hydroxide ion. Right, so we see that here. It says, how many times should the rate of the reaction be expected to decrease or increase when the pH of the system varies from 6 to 8? All right, so let's take a look. The rate has been shown to be first order with hydroxide ion, and the pH has gone from 6, where the pOH would be 8, to pH of 8, which now has a pOH of 6. So we go to the pOH is going from 8 to 6. So if we make a ratio of the rates of pH 6 to 8, pH 8 to 6, we see that if we put the concentration of hydroxide ion as 10 to the minus 6, right, because that's what the pOH gives us, 10 to the minus 6, divided by 10 to the minus 8, which is the pOH, when the corresponding hydroxide at that point, we see that it's 100 times faster. So this is how Unit 5, Module 3 and 4 can be asked on the exam. All right, well, let's take a look at some of the homework questions. So we did this one in class, but let's just make sure if you want to see it again. Let's take a look. So here we have a weak acid. It's HCN, hydrocyanic acid, and water. So we're expected to write a Ka. So let's remind ourselves that the Ka reaction, generic reaction, is HA plus H2O, making A minus and H3O plus. Every HA reaction will have H3O plus as its product. So we start with our HCN, and we add water, which is a liquid, and we see Cn, which is our A minus, right? This is our anion, our conjugate base, plus H3O plus. So here's the Ka reaction for HCN and water. When we solve for Ka, we have the products here, H3O plus times Cn minus divided by HCN. So that we see that the strength of the acid, which is its ability, which is a measure of how much H3O plus is produced in water when we see that it's directly proportional to Ka. The larger the Ka, the stronger the acid, the more H3O plus present in the solution. We can also rearrange this as we did in class, where we see that Ka, we could divide both sides by H3O plus, and we see that Ka divided by H3O plus is equal to the ratio of the conjugate base to the acid, which is really nice because since Ka is a constant at a given temperature, we can manipulate the pH, the H3O plus concentration in different ways to obtain any ratio of Cn minus to HCN that might be experimentally convenient. So if the H3O plus is less than Ka, we see that we'll have more of the conjugate base than the acid. If the Ka is less than the H3O plus, then we see we have more HCN, than more of the acid than we do of the conjugate base. So this is a really important analysis. You want to make sure you feel very comfortable with it. Okay, so this is the corresponding Kb analysis. So let's take a look at pyridine real quick, and we see that pyridine is a substance that has 5 carbons and 5 hydrogens. The hydrogens are non-acidic. And so when we write the hydrogen as H+, we connect it to the hydrogen, we connect it to the nitrogen because it's really important to distinguish that from the carbon hydrogens. All right, so C5HN. So remind ourselves, what is the Kb general reaction? We have base, a neutral base plus water here. If it's a nitrogen, we have base plus water to make BH plus OH minus. All right, so let's use that. So the corresponding the BH plus is the conjugate acid, and then the conjugate base of water is hydroxide. Using that here for pyridine, we see that we have here are the reactants, the base plus water, and then as products we have C5H5NH plus the corresponding conjugate acid plus the conjugate base of water, OH minus. Writing Kb for it, we take the products, OH minus divided by C5HN. We can then do we can divide both sides by hydroxide like we did for the acid, and we see that same type of relationship. That by controlling the hydroxide ion concentration, given that Kb is a constant with temperature, we can control the ratio of the conjugate acid to the base. If the hydroxide ion is less than Kb, well, we see that we have less of the conjugate acid than the base, and if the Kb is greater than the hydroxide ion concentration, we see the opposite, which is that there's more corresponding conjugate acid than base. So this is, again, something you want to feel very comfortable in terms of the analysis, and writing Kb, recognizing it, and seeing what the relationship is to OH minus, and correspondingly the POH, the pH, and what species would be present in greater abundance than the other. Okay. So here's a question that we did in class, and again, if you want to see it worked out and maybe a little bit slower, I'm presenting it here. So here we have two cases where ammonia is reacting with water, in one case as a base, in the other case as an acid. You're given two sets of data, the pKa of NH3 and the pKa of NH4+. So what we want to do is we want to recognize what those chemical reactions are of the data given to us. So the pKa of 35 is the case where NH3 is acting as an acid. That means that water is acting as a base. That also means that if water is acting as a base, its conjugate acid is H3O+. So we see that NH3 acting as an acid donates a proton to water. The anion that's formed is NH2-, and the conjugate acid of water, H3O+, is formed. The pKa shown of 9.25 is the reaction of NH4+ plus water, making NH3 plus H3O+. And in this case, we see that we have ammonium NH4+ reacting with water to make NH3 plus H3O+. The Kb, the pKb, which is 14 minus 9.25 for this chemical reaction, is NH3 plus water to form NH4 plus OH minus. This is the Kb, and what we see is these represent a conjugate system. This means that their Kas times Kb equals Kw for this system. So NH3 and NH4, when written this way, represent the Ka and Kb here. All right, so now that we have all this information, we can now go up to the top two equations and write in the corresponding equilibrium. So here we have ammonia acting as a base. Water must be acting as an acid. So there must be the conjugate base of water, which is going to be OH minus. And so the acid form of NH3 is going to be NH4 plus. This is the acceptance of a proton, making it NH4 plus. And then below we see that NH3 is acting like an acid, water is acting like a base, which means that its conjugate of water must be an acid, which is going to be H3O plus. The corresponding base must have donated that proton, leaving a negatively charged ion, which we see here as NH2-. That reaction will start first because it's given in the top line below, which is that we can just write 10 to the minus 35, right? So the K, the equilibrium constant, is, since the pKa is 35, we could just write as 1 times 10 to the minus 35. Going up to the top one, we see that this is the Kb that we wrote below. The Kb that we wrote below with the conjugate system of ammonia and NH4 plus is written here. So we can use the pKb from the derived from the pKa of NH4 plus. We do that, we see that the equilibrium constant for this reaction is going to be 10 to the minus 4.75 10 to the minus 4.75 after we subtract 14 from minus 9.25. You put that in your calculator, making sure to use the correct significant figures, and we see that 1.8 times 10 to the minus 5. That's how you do this problem. Please be careful. If you have 1.77 something, Sapling will mark that wrong. It's really important to follow the Ka story because oftentimes you'll be asked about Kb reactions, as we see here, given the Ka and pKa information. Okay, so the last calculation we'll run here is a pretty basic relationship between Ka and Kb. We see here we're given Ka of HBRO, and we just want to know what is the Kb for BRO minus, recognizing that it is the conjugate base of HBRO. So we use the relationship that Ka Kb equals Kw, and Kw is 1 times 10 to the minus 14 at 25 degrees Celsius. We can rearrange this for Kb, 1 times 10 to the minus 14, divided by 2.8 times 10 to the minus 9. Solving this, we get 3.6 times 10 to the minus 6 as Kb. Below, we see that given Kb for the trimethylamine, that's 6.3 times 10 to the minus 5. What is Ka for its conjugate acid? So keep in mind, it's conjugate acid. That means we can relate it to the Ka times Kb equals Kw. That's really important. So we'll do the same thing. Solving for Ka, we now put Kb below 1 times 10 to the minus 14 divided by 6.3 times 10 to the minus 5. Solving that, we get 1.6 times 10 to the minus 10. All right. So the last problem involves the last question in the quiz for Monday and Tuesday's lectures. There's a lot of questions regarding it, so let's go through it. So what we have is a chemical reaction where we see HC2H3O2 plus H2O making C2H3O2 minus, the acetate ion, plus H3O plus. So that's our generic Ka. And so we know the pH. The pH is given to us as 3.2, which means that we can immediately calculate what the concentration of H3O plus is, because it's going to be 10 to the minus 3.2. So going straight from there, we know that 10 to the minus 3.2. We put that in the calculator, and we get 6.3 times 10 to the minus 4. Now, given this chemical reaction, every time that an H3O plus is made, we must have made a C2H3O2 minus. Right? This is coming from the dissociation from HC2H3O2. The acid in the reactant side are making both of these conjugate acid and base pairs equally. So if we know that 6.3 times 10 to the minus 4 molar is the concentration of H3O plus, and there were some rounding errors on my part because of some assumptions I made, but the main thing is they have to be equal concentrations, right? There's no argument you can make that for the other answers that's correct. Each time one of these dissociates, you make one of each. We know how much there is of H3O plus, then we must automatically know how much C2H3O2 minus is there. Okay, so this crosses through many of the major concepts that are in Unit 6, Module 1 and in the homework. Please view this video as many times as necessary to make sure you feel confident with these concepts and you can apply them to the various Let's Think activities that we've discussed in class. All right, so good luck.